So if we want to figure out where the graph crosses the y-axis, the graph of f crosses the y-axis, what would we need to do? Yeah, so along the y-axis, x is equal to 0. So to find a point, one point on f of x equals 3x to the 5th minus 5x to the 3rd, it doesn't really matter what point we choose, but we need to have at least one point to kind of tack our graph down. So let's look at when x is equal to 0. Then f of 0 is 3 times 0 to the 5th minus 5 times 0 to the 3rd, which is just 0. And so what that tells us is that we can tack our graph down by putting a thumbtack in 0, 0. So here are our axes. And that last bit of information allowed us to stick a thumbtack in right at 0, 0. Okay, so let's go back up to our information and sort of map it out on our picture. The idea here is we want to be able to translate all of this information into a picture over there. One way to do this is to look at this information and say, okay, the intervals where f is increasing from negative infinity up to negative 1. And so I know during that interval, my function f is going uphill. And f is also increasing from positive 1 to infinity. So on this interval, f is also increasing. Now in between there, f is decreasing, our original function f, the one that we're trying to graph. F is decreasing from negative 1 to 0, and then from 0 to positive 1. And so from negative 1 up to 0, f is moving downhill. And from 0 to positive 1, f is also moving downhill. F is also decreasing. Okay, so if I were to be drawing a picture of this function, some other information that I didn't write up here, but that we can kind of see just from our first derivative information. Something else that I see is that I'm going to have a local maximum at x equals negative 1 and a local minimum at x is equal to positive 1. So I might write that information in here as well. So local max at x equals negative 1, local minimum at x is equal to positive 1. Okay, and we had that information from last time as well, but didn't write it up here today. So I kind of have a sense of what's happening with this picture. I know that my graph is going to be going uphill until I hit x equals negative 1, and then our function will go downhill. It's going to hit 0, 0. Then it's going to continue downhill until I hit x equals 1, and then my function will go uphill again. That's all I get from my first derivative. Now let's take a look at the second derivative. Our second derivative tells us that f is concave up on our interval from negative square root of 1/2 up to 0 and from positive square root of 1/2 off to infinity. Now, I think we mentioned this last time, but can somebody remind me what approximately the square root of 1/2 is equal to?
0.7.
So approximately 0.7. So I'm going to mark 0.7 on here as well. So negative 0.7 and positive 0.7. I'm really thinking of that as square root of 1/2 in both cases, but in terms of drawing my picture, decimals are helpful. Okay, so looking at my second derivative information, my information about f being concave up versus concave down, our function is concave up from negative square root of 1/2 up to 0. And also from 0.7 off to infinity. And our function is concave down on the other portions of the intervals. Okay, so from negative infinity up to negative square root of 1/2, our function is concave down. And from 0 to 0.7, or up to square root of 1/2, our function is concave down. Okay, so what I've done here is I've mapped out all of my information. Are there any questions about mapping out that information? Okay, so now I'm going to use that information to draw my picture. And it might help me to have some guidelines here. These are not vertical asymptotes. These are just some helpful guidelines for myself. Every time that I have a place where an interval breaks, I'm going to split up my x-axis. Okay, so let's start with our origin, since that's our thumbtack in our graph. Let's work from there over to the right first, and then we'll deal with this left-hand side. So from our origin, the place where we've stuck a tack into our graph, over to square root of 1/2, our graph is concave down and decreasing, so going downhill, and also the curve is concave down. So what I'm thinking about is something that looks maybe like this. So my graph is decreasing, f is decreasing, and f is also concave down. The curvature is such that if I put tangent lines, those tangent lines all occur above the curve. Okay, so now in our next interval from square root of 1/2 up to 1, well, what's happening in there, we've changed concavity, so we're now concave up, but we are still decreasing. So our function is still going downhill, but rather than being concave down, our graph is now concave up. There's a lot of black on here, so I'm going to make our function red. All right, so far so good? Okay. So now we've hit our next wall here, and at this wall, our function f is still concave up, but now our function is increasing. So we're going uphill with a curve that's upwards. So we get a picture that looks like this. Okay. Questions on the right-hand side of that picture? Okay, let's look at the left-hand side. Over here on our interval from negative square root of 1/2 up to 0, our function is concave up, but decreasing, so going downhill, but curving with a concave up type of curve. And so I might imagine something that looks like this, downhill, but concave up. And in the interval between -1 and negative square root of 1/2, we are looking at a graph that is concave down and decreasing. Concave down, and also going downhill, so decreasing. And last but not least, everything from negative infinity up to our first dashed line, our function is concave down but increasing, so we're going uphill, but the shape is concave down. And so we have something that looks like this. Oh, I
So when you have like conflicting things like concave up, but it's decreasing, you're going to have very subtle.
So if something, if you have a graph that is concave up and decreasing, then that's going to be a picture that looks like this.
Okay.
Whereas if I have concave down and decreasing, still my function is moving downhill, but now my curve is bowed in the opposite direction. And so the things that happen when we change, if our function goes from, so if I have something that looks like, I have some interval, and on the left half of the interval, my function is concave up, and on the right half, my function is concave down, but is decreasing all the way along, then what happens is that, that's not a very straight line. What happens is I have concave up, and then we switch to concave down. And so this point right here where we've changed concavity, that's our inflection point. Okay, so this is a graph of y is equal to f of x. And you should double check that. You should convince yourself by graphing f of x equals 3x to the 5th minus 5x cubed and see if you get a picture that looks similar to this one. Now the y-axis might not be scaled exactly the same, but you should get something that looks very similar to that. All right, are there any questions about drawing that picture? All right, so thinking about this particular example, just in terms of concerns about an exam, maybe. I mean, this problem took a really long time, right? I mean, it just took us about 10 minutes in this class, along with about 30 minutes in the other class to answer all this information together. So what does that mean for you as a student who may want to take a test and have a problem like this? Well, chances are really good that the question would be split up. I might say, determine the intervals where a function is increasing or decreasing, determine the intervals where a function is concave up or concave down. But then I might give you information like this to draw a picture. Okay? So I'm probably not going to have you put all of that information together in one big shebang, but if you can do that, then you've got it made. Okay. So with that being said, that completes this particular problem. Are there any questions on 4.3? I definitely want to talk about the even numbered one in there, number 14. Why don't we start with that?